Electric charge and electric field topic, wherein we look at the concepts of electric charge, electrostatic force, and electric field. First, let's take a look at the electric charge. While mass is a property of matter that brings about attraction-interaction, gravitational force being an attractive force, there's another property of matter that brings about both attraction and repulsion interaction, and that is the electric charge. Variable small q. Unit of charge is coulomb. Charge can bring about attraction and repulsion interaction because there are two types of electric charge. You have the positive charge and the negative charge. Just like mass, however, electric charge is a conservative quantity, meaning if there are several charges, total charge is the summation of all those charges. So if you have Q1, Q2, Q3, total charge is Q1 plus Q2 plus Q3. Here are some examples of particles with electric charge. You have the electron and the proton. Electron, charge QE is negative E or negative 1.602 times 10 to the negative 19 coulomb, where E is the elementary charge value, 1.602 times 10 to the negative 19 coulomb. It is advised that you memorize the quantities associated with the electron and the proton. Include as well the neutron. So you have QE, QP, and QN. And when it comes to the masses of these elementary particles, you have ME, MP, and MN. The interaction force between electric charges, whether attraction or repulsion, is referred to as the electrostatic force or simply electric force. The magnitude of this electrostatic force is given by Coulomb's law. Magnitude of F is equal to K times absolute value of Q1 times Q2 divided by R squared, where R is the distance between Q1 and Q2, and K is called the electrostatic constant or Coulomb's constant, 8.99 times 10 to the ninth power Newton meter squared per Coulomb squared. K has been shown to be equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity constant, 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. So that's for the magnitude of the electrostatic force. Force being a vector quantity, it also has direction. For the interaction direction, just take note of the following statement. Similar charges repel each other while opposite charges attract each other. When we say similar and opposite charges, we're talking about the polarity or sign of the charges. You will recall that there are two types of charges, positive charges and negative charges. So that means negative charge will repel other negative charges. Positive charge will repel other positive charges. While if they have opposite polarity, positive and negative or negative and positive, the charges will attract each other. So you have magnitude of the electrostatic force, Coulomb's law, and then for the direction, you have the interaction statement. Similar charges repel each other, while opposite charges attract each other. Now, since the two charges are separated by distance r, the question arises, How do the charges apply force on each other when they do not have any contact with each other? And the answer is the electric field. The electric field is produced by the electric charge. You can even consider it as some sort of a property of an electric charge because there is electric charge, there is electric field. The electric field is in the surrounding space and it is the electric field that exerts the electrostatic force. Since the electric field is in the surrounding space of the electric charge, the other charge is already in contact with the electric field. So the electric field has no problem applying or exerting the electrostatic force. The unit of electric field is Newton per Coulomb, and by convention, the electric field is directed away from positive charge and directed towards negative charge. The electric field is given by the following equation. E is equal to F over Q naught. Note that in the figure, you have the electric field and it is produced by charge Q. If you put a test charge Q naught inside the electric field, the electric field will apply force F on Q naught. E is equal to F over Q naught. The electric field is a vector quantity and the force that it will apply will either be in the same direction as the electric field or it will be in the opposite direction. It will all depend upon the polarity of test charge Q naught as you can see from the equation. E is equal to F over Q naught. If Q naught is positive, E and F will have the same direction. And if Q naught is negative, E and F will have opposite direction. Now, E is equal to F over Q naught. Again, E is produced by charge Q and E will apply force F on test charge Q naught, which is a distance r from Q. E is produced by Q. In terms of Q, the magnitude of E is equal to 1 over 4 pi epsilon naught, absolute value of Q divided by R squared. Again, R is the distance between Q naught and Q. If you remove Q naught, R is the distance between Q and the point at which you are determining the electric field. E is equal to 1 over 4 pi epsilon naught. Absolute value of Q over R squared is the magnitude of the electric field produced by Q. You will recall earlier, the direction of the electric field will depend upon the polarity of the charge that produced it. E, by convention, E is directed towards negative charge and directed away from positive charge. If there are several electric fields set up in the same area or location, the electric fields will add up. You have the net electric field E net is equal to the summation of the individual electric fields E1 plus E2 plus E3 and so on. The electric field produced by a single charge, Q, is constant only with respect to time. If you go from one location to another, you will see that the electric field produced by Q will have different magnitudes and direction. For an electric field to be truly constant, it must have both constant magnitude and constant direction. Such an electric field is referred to as uniform electric field. A uniform electric field, E is constant, which means that the force that it will apply on test charge Q naught will likewise be constant. And when the force is constant, the acceleration that is observed will likewise be constant. That means that any charge placed inside a uniform electric field will experience constant acceleration, will experience uniformly accelerated motion. And that's it for now. In the next video, we'll talk about the examples of electric charge and electric field.